In the first two videos of this series, I explained a quantity called the Kerma area product, and then I provided representative values that you can expect to encounter when you work in interventional radiology. In my final presentation, the fourth one, I'm going to talk about how I convert the Kerma area product into patient effective doses. And in this talk, I just want to explain what the effective dose is and why it's so useful in diagnostic radiology. Quite often I hear people say what we want are organ doses, and I profoundly disagree. Getting organ doses is actually trivial. I've just generated some values arbitrarily for CT exams. If you want to know what the breast dose is in a chest CT or the stomach dose is in an abdomen pelvic CT scan, I can provide them very easily. What you will find though is you've no idea what these numbers are. And if you do, I'd love you to explain it to me. I can generate these numbers, and I'm telling you, you can't interpret these numbers. But if you have a non-uniform pattern of energy deposition, as shown here for the chest CT scan, you can work out individual organ doses. So the lung gets 20 milligray, the breast gets 20 milligray, the stomach gets 10, the liver, the part of it that's irradiated, translates into a dose of 10 milligray. What do you do with this pattern of energy deposition? The answer is you calculate an effective dose. What you say is this pattern corresponds to every organ and tissue getting 5 milligray, and that means that the effective dose is 5 millisieverts. And so the effective dose is the equivalent whole body dose that has the same detriment in this patient. So if the patient gets the pattern on the left or the pattern on the right, the harm to the patient is the same. So it's a very elegant way of dealing with non-uniform patterns of energy deposition. You say these two for this patient have the equivalent harm. And now I can compare any exam with any other exam. How do I calculate the effective dose? I take into account how much radiation an organ gets and how sensitive it is. And the sensitive organs and tissues are the bone marrow for the induction of leukemia, the female breast, the lung, the colon, and the stomach. And if these organs and tissues are exposed to radiation, your effective doses will be high. If they're not exposed, your effective doses will be low. So for example, body CT scans have high doses, the head CT scan, or even though it uses much more radiation, has a much lower effective dose because the most sensitive organs and tissues by and large aren't being irradiated. So now if we look at these patterns of energy deposition, you calculate the effective dose and you see that the head, even though it uses much more radiation, CTDI vol is typically 60 milligray, the effective dose is a lot less than a chest and an abdomen, where CTDI vols are typically in the 10 to 15 milligray region. But you can now directly compare these values. I would say that your body CT scans typically have radiation doses, patient radiation risk, that are 3 or 4 times bigger than a head CT. We have on this planet natural background radiation. We're exposed to ubiquitous background radiation, cosmic, terrestrial, internal. We're exposed to radon. You add them all up, it's 3 millisieverts per year, and that is an effective dose that you can directly compare with the values I've just given you for CT scans. I personally like to categorize effective doses into one of 4 buckets. There are very low doses that are less than 0.1 millisieverts, like a chest x-ray, a skull x-ray, or an extremity x-ray. There are low dose exams like an abdominal x-ray, like a thoracic lumbar or an abdominal lumbar spine, and an extremity CT. There are moderate doses where a chest CT would be a good example, a GI-GU study, and a technetium-99m labeled radiopharmaceutical. The effective dose would be about 4 millisieverts, bang in the middle of this moderate range. And my final category is anything above 10 millisieverts. I would categorize as high. For example, a PET CT, a rather involved chest, abdomen, pelvic CT scan that has several phases, that would certainly fall into the high category. Here's an example of an IR procedure, a TIPS, and that would certainly fall into the high dose category. A TIPS procedure might be 30 to 50 millisieverts. We have regulatory dose limits. You as radiation workers carry badges to ensure you don't exceed a dose limit. The dose limits are given as an effective dose, and the current radiation worker dose limit is 50 millisieverts per year. We have workers, IR fellows for example, and I would expect them, when they wear 2 badges, to give me an accurate estimate of their effective dose. I would expect it to be about 5 millisieverts per year, or 10% of the current regulatory dose limit. So again, we have this quantity, the effective dose. It's easy to estimate values, and it gives you a really good idea of the amount of radiation in radiological examinations, and they can be compared with things like natural background and regulatory dose limits. Again, if people have questions, comments, concerns, by all means drop me an email at walterhuda@hotmail.com. Thank you.